Now let's explore a few fascinating properties of matrix multiplication. When multiple matrices are multiplied in sequence, it's just like applying a series of geometric transformations, one after another. On the screen, matrix C scales x-axis by 1/2 and stretches y-axis by a factor of 2. Matrix B represents a shear transformation along the horizontal axis. Matrix A corresponds to a 90-degree counterclockwise rotation around the origin. So the product A times B times C times the column vector x means first scale the x vector with C, then shear with B, then rotate with A. Please take note, the order of operations goes from right to left. Of course, we can also compute the product A times B times C as a single matrix, then apply that combined transformation to vector x. In that case, matrix multiplication A times B times C represents a composite geometric operation, everything done in one shot. Now consider a single matrix A. On screen, A times vector x gives us vector y. To understand this matrix multiplication, we can decompose this transformation into a sequence of familiar ones. Simply put, matrix decomposition breaks a matrix down into a product of simpler matrices. You can think of it as the reverse of matrix multiplication. For example, matrix A might be decomposed as rotation, scaling, then rotation. This is essentially eigenvalue decomposition, an important idea we'll explore later in the series. Or we might decompose matrix A as shear, scale, then shear. This type of decomposition is called LDL decomposition. Even if both A times B and B times A exist, in general, A times B is not equal to B times A. Sometimes, A times B and B times A don't even have the same shape. Even when they do have the same shape, they might still represent completely different transformations. Let's say A is a scaling matrix and B is a shear. Then A times B times vector x means shear first, then scale. But B times A times vector x means scale first, then shear. Clearly, these result in different geometric effects. But there are some special cases where A times B does equal B times A. If both A and B are 2 times 2 scaling matrices, then the order doesn't matter. The final result is exactly the same. Or if matrix A and B are both rotations around the origin in the plane, then once again, the order doesn't matter. The product A and B equals the product B and A.